So hopefully y'all had a good spring break, had a good week off. We have two main chapters, 2 chapters left that we're going to cover before the end of the year. One of them is chapter 6, this one here, that's going over exponential and logarithmic functions. 2 chapters left, then we're done with the year. Now, exponential logarithms, these two functions or types of functions are inverses of each other. They will undo one another. But before we get too far into that, the first things we're going to look at is exponential growth and exponential decay. We consider a function to be exponential growth if it's in the form of b to the x power, and the value of b is greater than 1. If the value of b is greater than 1, it's going to be exponential growth. B to the 0 is going to be 1. And go up here. And also, b to the x, the function, will never be 0. There's no way to put a number to a power and get it to be 0. It could be 1. We could put a number to the 0 power and get 1, but it itself cannot be 0. And part of the reason we consider these exponential, you don't have to write this part down. If we looked at, say, y equals 9 to the x power, we can look and see what happens. Because if I make a table of x, y values, we're going to go 0, 1, 2, 3, 4, and we put this to the power. 9 to the 0 power is 1. Anything to the 0 power is 1. 9 to the first is just 9. So really, we increase the value of x by 1, corresponding y values increase by 8. Now when x is 2, 9 to the second power is 81. So now we've increased by 72. The x is still increased by 1, but now the y increased by a factor of 72. Now 9 to the third So as we can see here, as the values of x, they're still increasing only by 1. The values of y are increasing greater and greater as we go on. Now if we do 9 to the fourth, 9 to the fourth power is now 6,561. Because we increased by 8, we increased by 72. Then we increased by 648, and then we just increased even more. Because if we said 9 to the fifth, we're now at 59,049. 9 to the sixth is 531,000. 9 to the 7, we're now at 4,782,969. 9 to the 8th. 9 to the 9th. And 9 to the 10th. Thousand, million, billion, we're at 3.4 billion. Exponential functions grow at this pace, and that's why we consider stuff to be exponential, because it's increasing more and more as time goes on. Wind force for tornadoes, hurricanes are considered exponential. That's why the scale goes 0 to 10. 0 to 10, even though, as y'all have seen, or especially seen pictures of, an earthquake with a magnitude of 5 compared to a magnitude of 4, even though it went up by 1, the amount of destruction and force does not equal what it's actually going up that 1 by. That's exponential growth. The other one we have is exponential decay. Exponential decay, if that value of b is between 0 and 1, focus up, then it's going to be decay. If that value is between 0 and 1, it's decay. If it's greater than 1, it's growth. Between 0 and 1 is decay. It's going to be decreasing. If we did the exact same thing, I'm going to use the graphing calculators table just so we can see multiple values at the same time. We'll say 1/9 since we use 9 for the first one. As we see the values here for 1/9, 1/9 is between 0 and 1. When x is -3, we have 729. 81/9, 1/9, 1/8, 1/9, 1 over 729. The numbers keep getting smaller and smaller. However, the one value that this cannot be is 0. We cannot put a number, we can't multiply a number by itself any number of times and get 0. It just does not work. Questions on this so far? All right, let's look at these here. For these four here, we want to determine 1, is the function exponential growth or exponential decay? And 2, what is its value when x is 2? Now we look at a, y equals 2 to the x. What is the value of b for this here? 2. Is 2 bigger than 1 or between 0 and 1? Bigger than 1. So this is growth. It's growth because the value of b is greater than 1. Now we need to figure out if, or what the value of y is when x is 2. So we're going to replace x with 2, so we have 2 squared, and 2 squared is 4. Questions on letter A? Let's look at B. Y equals 1/2 x. It is decay because the value of b is what? It's less than 1 and greater than 0. Now we need to evaluate it when x is 2. I don't know why I put x again. So at this point here, we could plug it in 1/2 squared. So we're saying 1/2 times 1/2. So 1 times 1 is 1. 2 times 2 is 4. Questions on either one of these here? Questions on either one of these so far? Now, one of the things I will also say, because do not write this down, this has nothing to do with any of this here. Let's make it a little bit nicer. Y equals -2 to the x. Would this be exponential growth or exponential decay? It would not be growth. It would not be decay. It would be neither. It's actually not really a function. Well, the issue is, and once we look at the table, it'll make more sense. Anything to the 0 power is 1 besides 0. So -2 to the 0 is 1. -2 to the first power, well, what did we just do? We went from +2, so it jumped from one side to the other. That's fine. Add 2, it goes to 4. 3, -8. 4 is 16. Add 5, as we talked about function in just a minute, it has to pass the vertical line test for it to be a function, and it cannot have jumps, holes, or edges. So by definition, absolute value is not technically a function because it has that hard edge. Actually, it can be a function, but this here is jumping from above to below. It's jumping from positive, negative is not a function because it's doing this jump. Does that make sense? I thought about it with negatives originally. I'm like, oh, this works. And no, because even if we tried to graph it, clear that out, -2. Because it's doing this jump back, forth, it's not a function. It can still give us a table, but it's not a function. Let's look at A. Y equals 1.3 to the x would be growth. Yes. Then we just need to put parentheses 1.3, close parentheses to the second power. We're going to square it. We can do it by hand, or we can let the calculator figure out what 1.3 squared is, or 13 squared. Move the decimal 2 spots. We get this here. How about B? Decay because 1/3 is between 0 and 1. And indeed, 1/3 squared, 1/3 times 1/3 is 1/3. Questions on any of this so far? Next 4, we're just going to say growth or decay. We're not going to worry about evaluating these here or plugging them in. We're just going to go through them. Number 1, y equals 4x would indeed be growth, because 4 is indeed greater than 1. 2/3 to the x indeed would be decay. 0.25 indeed would be decay, because 0.25 is indeed less than 1, greater than 0. And 1.5 is greater than 1, so it would indeed be growth. Questions on 1 through 4? Now, the other type of base that we can have is E. E is an irrational number. It's a non-repeating, non-terminating decimal. And it can be expressed by the expression 1 plus 1 over x to the x. It approaches our base E, this nice number. Not really a nice number in and of itself, but especially with logarithmic functions, it works very nicely. Now, E, even though it is an irrational number, we can pretty much treat it the same way we treat variables in a lot of aspects. Such as if I had e to the 3rd times e to the 6th, it would indeed be e to the 9th, because when we multiply like bases, we add the exponents. Now, for the most part, e is going to have a little bit of a variation because it is a non-repeating, non-terminating decimal. But what we're looking at is e to the 6th times e to the 3rd, because if we hit second and then the LN button, it brings up e. So it tells me that the decimal approximation is 8,103.083928 going on and on. And we found it to be 8e to the 9th, which is the exact same thing. Now, all the way at that last digit, there are some times, just because how the calculator does it, for whatever reason, it might be one off, but we are indeed working with irrational numbers. So there is some pixel error, some calculation error, because with some of these here, it's looking more at the graph, or essentially the graphical approximation, or however it's going to calculate it. Can be some errors in there. But I would be using it not so much to check it, it'd be more to check it than it is to actually find the value. Because here we just add 3 and 6 together to get 9. It is indeed e to the 9th. B, 16 e to the 5th divided by 4 e to the 5th. You can divide the numbers first. 16 divided by 4 is 4. E to the 5th divided by e to the 4th. When we divide like bases, we subtract the exponents. Even though e is a number, we can still use that property. 5 minus 4 is 1. Is it bigger on top or bottom? Top, so it's going to stay on top. If you're having to plug in e as a value, so e for e, if we were trying to plug that in to get the decimal approximation, the calculator will still need an exponent for e. So we'll have to plug in 1. Calculator is going to have e to the first power. It is set so that it needs it. As much as I want to just say second e, it has to have it even if it is just 1. It has to have that exponent. Questions on A or B? We already looked at C. E, 3e to the negative 4x squared. Powers of powers, multiply. So our e is going to be to the negative 4x times 2. Now our 3 is going to be 3 squared, and that's pretty much as we've said it, and that's pretty much we'll always say it. However, the exponent attached to 3 is 1. It's really 3 to the first. So really what we're doing is 3 to the 1 times 2. 1 times 2 is just 2. And for simplicity's sake, thank you. Sometimes words just don't come. We don't write 1 times 2. Because that for some is going to be more confusing than just say it's 3 squared. It is what we're doing, but we're just leaving that step out. Now 3 squared is what? 9. E. So we have to multiply the negative 4x and 2. Negative 4 times 2 is? Negative 8. We are still multiplying it with the x, but it really doesn't have anything that's affecting that product, so it's still just going to sit right there. Questions on how we got 9e to the negative 9 or negative 8x. We can't leave an exponent negative. To make it positive, we got to move it from the top of the fraction to the bottom. Because when we move a term from the top of the fraction to the bottom or bottom to the top, the exponent goes from positive to negative or negative to positive. The exponent sign is the only thing that's changing, not the number. It's not going to go from having positive e to negative e. It's the exponent that's changing. If they have a question like this on the ACT, they will definitely put negative e to the 8x as a possible answer choice. Just to see, are you going to change the sign of e, not the exponent? Questions on ABC? We're going to look at D here in a second. Let's look at 1, 2, 3. E to the 7th times e to the 4th. 7 plus 4 is 11. So this here would be e to the 11th. This is the one I was specifically talking about, because we can go e to the 7th times e to the 4th. For whatever reason, rounding of sometimes change that 1 to a 2. And the reason for that is e to the 11th, it being a 2, is going to be a more precise answer. Because, and I'm realizing this now, what my best guess, I don't know for sure, is that e to the 7th, it did an approximation of e to the 7th times an approximation of e to the 4th. Since we rounded before we multiplied and then rounded again, it's going to throw that answer off slightly. Yep. Graphing calculator is a little more nice. Yep. So that's a better approximation of this here. But still works. It gets us close enough. Let's look at number 2. 24 over 8. 24 divided by 8 is 3. If it doesn't reduce to a nice number, we can leave it as a fraction. Nothing wrong with it. E to the 5th is we're dividing it by e to the 8th. E to the 8th over e to the 5th. When we divide like bases, we subtract the exponents. 8 minus 5 is it bigger on top or bottom? Top, yes. So it's going to stay on top. If the e to the 8th had been on bottom, and it was, so e to the 5th over e to the 8th, we still say 8 minus 5 is 3. Since it's bigger on bottom, it will stay on bottom. So if they had been flipped. Does that make sense?
Wait, is that why we didn't do it on the first one on E? For the top one?
Because e to the 5th divided by e to the 8th, 8 minus 5 is still 3, yes? But since it's bigger on bottom, it's going to stay on bottom. And more, if we did it by definition, by the definition of dividing like bases, it would be the base, whatever it is, to the top exponent minus the bottom. Well, 5 minus 8 is negative 3. But to make it positive, we've got to move it back to the, if it's bigger on bottom, it's going to stay on bottom. Questions on 1 or 2? Yeah, no, we still moved it on top for the one. This one here is what, or why we moved the one to the bottom. It's because it was negative. Okay. Number 3, 10e to the negative 3x to the third. So we're having to apply that power of 3 to both terms. Now for the 10, again, it's still 10 to the 1 times 3, but 1 times 3 is just 3. E to the negative 3x. Powers of powers again, multiply, so we're going to be multiplying the negative 3x by 3. Now 10 to the third is 1,000. E, so our negative 3x times 3 is going to be negative 9x. And lastly, to make that exponent positive, we've got to move it from the top of the fraction to the bottom. Questions on ABC? 1, 2, 3. All right. If we're good with those there, now we'll look at D and number 4. Now, I know we've talked about it, especially in Algebra 1. We've talked about it before. One of our properties of radicals says that if we have 2 or more things, 2 or more terms being multiplied together inside of a radical, we can rewrite it as a product of those radicals. Same thing is true if we're multiplying 2 radicals together, we can multiply what's inside. And I do this here for a certain reason. One, we know how to find the square root of 16. Square root of 16 is just saying what times itself is 16, and that is 4. So we're good there. Now the hitch is trying to figure out what times itself is e to the 4x. Okay. Now, I know Algebra 1, y'all went over this in a little bit form. But the nth root of a to the x, we're going to deal with it here. We're going to dig more into it in chapter 5. But the nth root of a to the x is equal to a to the x over n. This is actually very interesting because for the most part, in a few places we haven't talked, or you talked about a little bit, if you came across something like this here, the fourth root of a to the fourth, or the square root of x squared, a squared squared, for the most part, not every case, what did we say? Those are the same, so they cancel out. It's just a, we moved on. For the most part, not every case, was there not much explanation besides that. I mean, there's a little bit here and there, but this has been it for the most part. Yes? Okay. Now, by this definition, this works with all radicals. That's telling us this is the same as a exponent. The exponent attached to a goes on top. The index, what root we're taking, goes on bottom. So the fourth root of a to the fourth is a to the 4/4. What is 4/4? It's just a to the first, or just a. This is why that cancels, why we can just go, we cross those out, we're done. And we can treat this with any exponent. This works with all exponents. Now it's like, well, why didn't we introduce this the first time? Well, in middle school, you're starting to learn radicals can have more than one root. We're doing good with learning radicals, and learning exponentials with radicals is a bit of a stretch. It's a bit too much to learn all at once. So, if we look at the e to the 4x, according to that there, we still have the e. What's inside? This exponent goes on top. And even though we don't have it written, the root, the index is understood to be 2, because it's a square root. So really the square root of e to the 4x is the same as saying e to the 4x divided by 2. Well, 4 over 2 is 2. So it's really e to the 2x. Questions on this here? We ready for the next one? Cubed root of 64e to the 9x. Well, we can do a similar thing. Cubed root of 64 times the cubed root of e to the 9x. Now, cubed root of 64 would be 4. If we're not sure, either calculator will do it. 3 second x root 64 is e. Number on top comes the exponent inside the radical, or it could really be the exponent outside the radical, depending on how it's written. But that's the number on top. The number on bottom is the root. So we're really saying we have 9x over 3. Telling us that simplifies 4e to the 3x. Questions on this here? I don't know about y'all, but using the graphing calculator, especially finding cubed roots or finding cubed roots in general, is not necessarily the easiest thing to type in. What would this have been if I wrote the cubed root of 64 as a fractional exponent? Because an exponent here is understood to be 1. The root is. So we're saying if this property works, the cubed root of 64 should be the same as 64 to the 1/3. Both work. Last piece, last thing we're covering today. The function y equals a e to the rx is called a natural base exponential function, where a is a positive number. Because again, multiplying it by a negative doesn't do a whole lot. It flips it upside down. It does some different things. And r is either greater than 0 or less than 0. The exponent's either going to be positive or it's going to be negative. It's going to be one of those two. If the exponent is positive, doesn't matter what the number is, if the exponent attached to e is positive, it's going to be growth. Because the base is already greater than 1. E is set to be 2.718 going on and on and on. So if the exponent is positive, we're good there. Now, if the exponent is negative, it is going to be okay. Because y equals e to the negative x. To make that exponent positive, we've got to move it from the top of the fraction to the bottom. So now our b value is actually between 0 and 1, because it's 1 over 2.178. It's now going to be decay. And yes, this isn't written in the exact same form of b to the x, but luckily with our properties of exponents, we can actually rewrite it as 1 over e all to the x. Seems weird we can do that, because if we applied that power of x back in, we'd have to do it to the top and bottom. Well, what's the number on top now? 1. It doesn't matter what I multiply 1 by itself. No matter how many times I multiply 1 by itself, it's still just 1. So we do have 1 over. All right. So what do we think? Y equals 3e to the x. Growth or decay? Growth, because the exponent is positive. What do you think about b, e to the negative 0.5x? Decay, because that exponent is negative. It has nothing to do with the 0.5. How about number 4? Growth. The exponent is positive. When that base is e, we're not worried about the number, because e is set to be 2.718. Number 5. Decay, because we do have e. We look at the exponent, and since it's negative, it would be decay. And number 6, growth. Not so much because of the 2, but because it is positive. And that is, yeah. By the way, guys, there is a front and back. So, problems 1 through 4. 1 through 4, you're going to have 2 answers on each. 1 through 4, evaluate each expression for x equals negative 2 and x equals 3. So you're plugging in negative 2, seeing what the value is, doing the same thing for 3. 5 through 14, Determine whether each function is growth or decay. That's it. Literally, you're just saying it's either growth or decay. On the back, 15 through 18, simplify it. Like we did with the e's, those expressions simplify down. And lastly, 19 through 24, determine if it's growth or decay. That's it. It is a longer worksheet than we normally have, but shouldn't take y'all too long to knock that one out.